So I'm guessing we're live. All right, well, how's everybody doing? Did you guys like your first session? Excellent. Well, today I'm going to be talking about picking the right size of your various system components and different ways that you can go about sizing things for your piping system. And one of the ways I really like to start off with is just bringing about awareness that up to 60% of total electrical energy usage that gets consumed is due to pumping systems in various industrial processes. And so if you think about it, when you put a pump into operation and then you immediately have a downstream valve that throttles to get you the flow that you want, you're immediately wasting money and energy right there. It's like driving with your foot in the gas pedal and the brake pad at the same time. And so you want to make sure that your components and your pipes are sized properly for your system in order to help save money and energy. And so today I'm going to talk about how to size pipes, pumps, valves, orifice plates, heat exchangers. I'm going to talk about how to do energy cost calculations, and that can show you how much money you are able to save by using a VFD versus flow control valves, for example. I'm going to talk about how to set up and calculate full system costs with Fathom. And then we're going to talk about methods on how to actually minimize those costs at that point. And so what I'm going to start off with is a very simple example here. We have a pumping system where we want to deliver water up a hill at 500 gallons per minute. We know that the pipe material is going to be steel, but we don't know what size we need yet. So the first step that we're going to do is to size the pipes in order to maintain to limit the velocity to be 6 feet per second. We don't want it to be any higher than that. And so with that, I'm going to go ahead and open up Fathom here. She rearranged all of her icons, so now I need to find where stuff is again. Let's see. Now, it tells you that the total amount of piping that you have to work with is 1,000 feet of pipe. And so you have to make an assumption on your suction versus your discharge. So we're just going to assume 10 feet for suction pipe and 990 feet for the discharge pipe. Okay, so I'm going to go ahead and build a model from scratch here, which is going to be really quick. First thing you need to do is define your fluid properties. So I'm going to use water at 1 atmosphere, 70 degrees Fahrenheit. Calculate my properties. Click OK. If I open up my checklist here, I can see that that item is now finished. Next thing I need to do is actually draw my system. So I've got my first reservoir, my pump, and my discharge reservoir. I'm going to play connect the dots. And there we go. Next thing that we're going to do is define our boundary conditions. So our reservoir for the supply end is going to have a 10-foot liquid surface elevation. So that's at 10 feet. And I'm going to put my pipe at the bottom of the reservoir, which is going to be at a 0-foot elevation. I'm resetting all the parameters to be default Fathom because it was kind of not that. Okay, the next thing I'm going to do is I'm going to define the discharge reservoir. This is going to be at a 200-foot elevation. So 200 feet, and we'll just keep the pipe at the bottom or the top of the tank at that point there. Click OK. And then finally, we need to specify the pump. And so you could do a pump curve, but we don't know what the pump curve is yet. So we're going to start off with just a fixed flow rate because we know we need 500 gallons per minute. You could start by sizing the pump first, but you'd have to know what the pipe diameter is. So that's where I'm going to figure out the pipe diameters first. The pump is also going to be at a 0-foot elevation. Now that our system here is built, I need to define the pipes. And you could simply define just your inner diameter, your length, or your friction model directly, or you can choose from one of our pre-built pipe material databases. And so I'm going to choose from the drop-down menu and choose steel. And I don't know what the pipe diameter is going to be, so I'm going to start off with just a guess of 3-inch diameter. And this is going to be a 10-foot long pipe. And I click OK. That pipe is defined. And then I'm going to define the discharge pipe as well. Same diameter, 3 inches. And I'm going to use 990 feet for my pipe length. And I'm going to add on an additional K factor because perhaps this pipe is not going linearly. It might be turning all over the place. I want to account for those additional fittings without having to actually model them. So I'm going to just specify a total K factor of 25. Click OK. And now we are all done and we are ready to run the model. However, what I'm going to do next is I'm going to open up each of these pipes and I'm going to display the pipe nominal size on the workspace. That way we can see which systems are which. I'm going to make the text a little bit larger here. Colors and fonts. Make it 14. There we go. That's a lot easier to see. Now, I could do different scenarios of different pipe diameters, but there's a different way to do it as well, where I'm going to take these pipes and junctions, and I'm going to do a duplicate special. So that's basically copy and paste in one, but doing it in the special way allows you to offset the numbers. That way the numbering scheme is consistent. So I've got, pipe 1 corresponds with pipe 11. And so on and so forth. So here's my second system. My second system, I'm going to use 4-inch diameter pipe for both of these. And then finally, I'm going to duplicate the system one more time. Edit, duplicate special. Offset it by 10, click OK. And this last system I'm going to use 5-inch diameter. So we got 5 inches there, 5 inches there. Okay, so when I run the model, I'm going to look for the pipe size that gets me below 6 feet per second for the velocity. So I'm going to go to my output control window and I'm going to set up some custom output here. I'm going to remove the name of the pipe and I'm going to put velocity above flow rate and I'm going to add nominal pipe size to the list. I'm going to move that all the way up to the top. There we go. And it's going to make me save the model before I run it. Oh, come on. All right, we're going to give it a name. Pipe and pump sizing. Now, one thing to remember, this is Professor Pumphead. He's going to give you tips on how to size your pumps properly as well as your pipes. So remember, high velocity leads to high pressure losses. Okay. So when we take a look here at the results, I can see that definitely 3-inch diameter pipes, not going to work. Velocity is 22 feet per second. 4-inch diameter pipes is better, but it's still too high. Same thing with 5-inch. Sorry about this, I've got things popping up. We had to switch computers today, and we've got all these things that are popping up that I don't know about. Okay, so it looks like we got to go 1 inch higher up to 6 inches. So all you need to do is just go back to the workspace, and then with that system you can duplicate it again. And then this is going to be 6-inch diameter. Rerun the model, and ta-da, the velocity is now below 6 feet per second. So I've just sized my pipes in order to keep within my design constraint of being less than 6 feet per second. Now at this point, since I've sized my pipes to get the appropriate velocity that I want, I can now go about sizing my pump. And so for that, I'm going to do a child scenario, pump sizing. And for pump sizing, it's really simple. You would look at your pump results, which are right up here at the top, and you can see for each of these cases what the flow rate and what the resulting head rise needs to be. So with the larger diameter pipe, you need only to overcome 218 feet of head for your pump in order to deliver that flow through the system. You could take this operating point to a manufacturer and they'll give you a pump curve, or you can search directly within Fathom itself. And so if you click on this little pump icon with the spark coming out of it, that's the size of pump button. So when you click on that, I'm going to use pump number 25 as my reference, because I want to make sure I minimize the head rise that's needed and the power draw. And I'm going to search the internet for a pump curve that will fit. And so after I choose internet, that's where I'm going to go. I'm going to click on search, and then you pick a manufacturer to work from. And so we have a list of manufacturers that you can use. I'm going to start with Berkeley Pumps and see if they have any pumps available. And I'm just going to open up a web browser. Which is using my hotspot on my phone for this. It contains your operating information here. The next thing I'm going to do is click on next. And then you would specify a product line, which I'll choose just a few of them just to give me some variety here. And then click next. So this web browser, this is IntelliClip's interface. IntelliClip is another company that we work with, and they are able to select from a wide variety of pump manufacturers to get you a pump curve. And so this is the interface of them that we're using right now. Now when you go to select your pump, you're going to want to select a pump that's operating fairly close to the best efficiency point at that flow rate, and that you have a relatively high efficiency for your pump as well. So for that one, I'm going to choose this pump right here. And when you click on that, it contains all of your pump spec sheet information. And then you can also download this as a PDF if you wanted. But what you need for Fathom is a special file. And so for that, you just click on download. And that downloads this IQX file. And so I'm going to move this so that it's easier for me to find. Okay. So now that I downloaded that IQX file, I go back into Fathom and I go to step number 2, which is to open up that file. When I click on open, I can browse to that file there, IQX, and just open it up. That's what my pump curve is going to look like. And I want to apply that pump curve to my very bottom pump in that system. And so what I'm going to do is I'm going to click on apply pump data. And I'm going to physically change that pump junction. So I click on the pump I want to change right here. I'm going to apply it. So now when I go back into my workspace here, this pump is now using that pump curve. And you can see that it's based upon an RPM of 2,632 RPM, and it is a 10.4-inch impeller trim. Now, in my pump sizing scenario, I only care about this system on the bottom here. And so for all the rest of these, I'm just going to delete them to get them out of the way. All right, so we're going to run the system here. Now, we take a look at our pump summary, and we can see that at 500 gallons per minute, we're operating at 218 feet of head, which is very close to our original operating point. And you also have other information such as how much power you're drawing. And I'm not sure why it's not doing my BEP calculation. There we go. Sometimes if you just reopen a window and click OK, it'll do what you want it to. And so you can see here that it's operating at about 99% of the best efficiency point. It's going to be a really solid operation, not going to be having a lot of vibrational problems and whatnot, and you're getting an efficiency of about 75%. So that's how you go through and size the pump. That really is all there is to it. Is sizing your pipes in order to stay within a certain criteria, and then once you get that criteria met, use those pipes to be able to size your pump. Now, when we talk about pipe sizing, there's more to it, because you don't just want to size the pipes to get a right velocity, you want to make sure that you have an overall minimum cost. And we're going to talk more about cost calculations later in this session and how to minimize those costs all at the same time. So from right there, I've just accomplished these two first slides of sizing pipes and how to go about sizing your pump. That's all there is to it. Does anybody have any questions on any of those steps?
Do you have any recommendations for sizing like a sump pump or a water pump?
Well,
Sorry if that takes you completely off topic.
no. So this is a bit more robust than the different kinds of pumps. Once you get to the point of, if you're trying to size a sump pump or a vertical turbine pump, I mean, all that Fathom cares about is what's the pump curve look like. Fathom doesn't know what kind of pump you have. And the only thing that would really matter is just the connection of elevations for your inlet and outlet and where your suction and discharges are. But in the end, a pump curve is a pump curve.
So if we do the inlet of the pump, like, 10 feet lower than the outlet, that should model a sump pump.
Yeah, that could model a sump pump. And so, but when you do that, it all depends on where they're measuring their pressure head. And so if you have your suction here and your discharge is way up here, if they put their pressure gauge at this point, then you would enter this as your outlet elevation, and for your junctions you can do a different inlet and outlet. So if they have the pressure gauge right here, then that would be applicable to that. But more often than not, they're probably going to have the pressure gauges really close to each other, right where the pump bowl is itself. And then the pump manufacturer is going to supply that column piping, but if they're getting their curve based upon this, then you want to actually model that column piping as additional piping at that point when it comes up and then out of the ground. Now in Fathom 9, you do have the ability to model submerged pumps, and it's really easy. All you would do is drop a pump on the workspace, and then when you open up the pump, you would use this option to model as a submerged pump, and you would either directly specify the suction pressure at your impeller, or you can specify a pump head or HGL. Now, this is confusing, and so I wrote a blog on this. If you go to our website in AFC.com and under the Learning Center, and then go to Tips and Tricks, I talked about this concept here. The value that you specify for the head HGL is going to be the liquid surface elevation of the reservoir that your pump is submerged in. So if you have a pump that is 10 feet below a liquid surface, but let's say that you're at the Rocky Mountains, you're at the top of Rocky Mountain National Park, and so let's say that your elevation of your pump is at 10,000 feet at your pump suction, but your liquid surface elevation is 10,200 feet. What you're going to do is you're going to specify the inlet suction being 10,000 feet, that's where it is, and then by doing the math in your head, since you have 200 feet of liquid head above your pump suction, you're going to specify what the true elevation is in that case. You're going to specify 10,200 feet. So when you specify 10,200 feet, that's how Fathom figures out between these two values that you've got 200 feet ahead above that pump. So it's the true liquid surface elevation reference of your system for the reservoir that your pump is submerged in. And again, my blog talks all about that, and so it'll give you some good examples for that. Does anybody have any other questions on this? Now, let's talk about how you can size valves and orifice plates. Let's say that you have a gravity flow system right here, and for the gravity flow system, there's a lot of stuff that you can size with this. You can go through the same type of pipe sizing analysis that I did, where it tells you that your desired flow is 250 gallons per minute, and you want to make sure that your control valve maintains at least an 8 psi pressure loss across itself so it can maintain good controllability for its lifetime. And we've got 200 total feet of pipe. We're going to size the pipes. We're going to use the control valve to figure out how to size a regular valve, how to size an orifice plate, and it's going to be exciting. So I'm going to go ahead and open up a new model here. All right, so first step is to define my system properties. So that's going to be water at 70 degrees Fahrenheit. And then I build my system, reservoir, control valve, reservoir, plate connect the dots. Okay, so my supply reservoir is going to be at a 40-foot liquid surface elevation, and it's going to have the pipe depth at the top of the tank, which is fine. I'm going to reset my okay. If you turn on this light bulb, it'll highlight labels in red for things that are not fully defined. So that'll help you figure out what needs to be specified. Next thing is going to be my discharge reservoir, and this is at a 10-foot liquid surface elevation, open to atmosphere. For my control valve, you can do this in two different ways. You can either set a flow control valve to be equal to 250 gallons per minute. That's our flow requirement. And then you would check the resulting pressure loss across the control valve that results, and then you can do it that way to size your pipes. Or instead you can do a constant pressure loss where you'd specify 8 psi as your pressure loss, and then make sure your flow rates match in that case. So multiple ways to skin the cat. I'm going to use the flow control method here. Do you have a question? Oh, okay. All right. And so here I'm going to start off with steel pipe. And I'm going to start off with 3 inches, 100 feet. Now, if you have another pipe that is going to have exactly the same values, and you don't want to have to re-enter anything, just click on this drop-down menu to copy data from pipe. I'm going to copy all this data from my initial pipe, and there it is. So I'll save you some time there. Okay, so here's my system. I also want to make sure I show my nominal size in the workspace. Let's see. Not on the workspace, but on the visual report you can. So if you go to visual report, this is the visual board is mainly for output, but you can do it for input too. And so you can do length and nominal size and maybe elevation for your junctions. And that'll overlay that information right on top of your model. Down the road someday, we want to try and combine the workspace and the visual report together. And actually, I think it started off that way back in the very early days of Fathom. And that was able to be done through one of the graphical tools that they used at the time. And then with the newer graphical tools, they couldn't do that. So they had to separate them into different windows. But we want to try and recombine them again down the road at some point. Okay, so here's my system for 3 inches. I'm going to do my duplicating again. Okay, there's my system, and I'm going to do this as 4 inches. And we'll do one more. And this will be 5 inches. Okay. And then set up my output control to include the nominal size. All right. So now when I go to run the model, I'll just call it valve sizing, because ultimately that's what we're going to do. That's way too big. Okay, so we can see that we're getting flow rates of exactly 250 gallons per minute through all of our different sizes, because that's what we specified. What we care about is what's the pressure loss across the control valves. So if you go to the valve summary tab, you can see that the pressure loss is 1 psi, 10 psi, and 12 psi. And so again, that's going to be based upon the 3-inch system. So when you use a 3-inch pipe size, that's going to be taking out a whole bunch of pressure loss right there. And then if you have a 4-inch pipe size, then you've exceeded your minimum, which is what you wanted to do. It's at 10 PSID. So you're going to use the 4-inch diameter pipe size for this system. You could try and get it down between 3 inches and 4 inches, but then you're going into non-standard pipe size territory. So that's where you would stick with the 4-inch diameter pipe size in this situation. Now, there is additional information here that you can look at, and that is the resulting CV values. When a control valve is used, whether you've got a pressure set point or flow set point, Fathom is going to determine what your pressure loss needs to be in order to meet your set point. Once your pressure loss is known, your flow rate is known, the CV value could then be calculated. And that CV value, this could represent a valve that you need to go buy from any manufacturer. Because if it's just going to be a manual throttling valve, you're not actually intending for it to control, this size is your valve for you. So that's the CV that you need. Now let's talk about for an orifice. If you're trying to use an orifice plate instead of a valve, there are additional parameters for control valves that are useful. So if you go into your output control window and then go to valves, I'm going to specify equivalent orifice area and equivalent orifice diameter. And so what this does here is it tells you that for the equivalent orifice diameter, that's your orifice diameter that you would need based upon a sharp-edged orifice with a discharge coefficient of 0.6. So we can see that if we're going to use an orifice, that's our diameter that we need. So here's what you can do next is you can make another scenario where you specify those values as a regular valve or an orifice junction. So what I'm going to do is I'm going to create a child scenario here, and I'm going to delete the top system. I'm going to delete the bottom system. And so what I'm going to do at this point is I'm going to take this system and I'm going to duplicate it. And instead of using a control valve, I'm going to use a regular valve. Here's how easy it is to change one valve junction into, or one junction into another. It's our morph capability. So if you hover over a junction, hold the control key down, then while holding control, click and drag the valve or the junction on top of the one you're replacing, and that'll morph it. So now all I need to do is open up this valve here, and for the CV value, what was it, 63.8 or something? We'll start with that. And then I'm going to duplicate this system one more time. And down below, I'm going to use an orifice plate. Here's my orifice. I'm going to morph that into an orifice. And so I'm using a sharp-edged orifice right here. My diameter, 1.983 inches, was it? Actually, you need to do user specify because you need the discharge coefficient to be 0.6. So again, if you're doing these values, then all your results for each system should match. So now let's go ahead and rerun the model here. So let's see, my control valve, the CV, oops, that was the wrong one. It's a 78.89. I think this is 1.938 inches actually. Okay, there we go. So when you compare the original control valve results with your regular valve results, you can see that they match exactly. So this shows you how you can use a control valve in order to size the regular valves in your system. Then if we go to our orifice results down here, you can see that your flow through the orifice is right at 250 gallons per minute. And if you look at the loss factor, 37.6, that should match the loss factor of the valve, which it basically does. And so that's how you'd be able to size pipes and valves and orifice plates. Very simple stuff. Same thing with sizing pumps. Any questions on that? Oops, I'm going to turn off Aaron's emails. Okay. One more sizing example, then we'll talk about cost calculations. So here, this is a situation where you want to size a heat exchanger for thermal effects. So I'm going to go ahead and open up this model here. Okay, so I have a very basic system where I'm modeling a refrigerant, R11, and I've got my pump. I am modeling heat transfer in this, and so initially you don't know what the heat rate is for your heat exchangers. So what you do know is the outlet temperature that you want to achieve, which is going to be 75 degrees Fahrenheit. So what you would do first is you would specify 75 degrees Fahrenheit for each heat exchanger, and then run the model. And after you run the model there, you take a look at the heat exchanger, and in order to get 75 degrees Fahrenheit, the heat rate needs to be about 640 BTUs per second for each heat exchanger. So now you've got your heat rate that you need in order to achieve that. That's your initial sizing for your heat exchanger. But there's a little bit more that you can do with getting a bit more of a realistic thermal model in there. So let's say that we have counterflow heat exchangers that we're modeling. This time it's a bit different. Let's say that I actually know what the heat transfer area and overall heat transfer coefficient is, as well as my flow rate on the other side of the heat exchanger and the specific heat. So what I need to do is I want to iterate on one of these parameters that I have flexibility in being able to change in order to match that original heat rate, and that will give me the outlet temperature that I need. So in this case, the parameter that I'm going to iterate on is the inlet temperature on the other side of the heat exchanger. And so that other side is why I am not actually modeling, but I'm still able to account for its effects here. And I'm going to do that with the goal seeking control module, and that will automate the process for me, and it will save a lot of time. So under analysis, when you go to activate modules, you go to tools, and then activate modules, and then you just check off the boxes for the ones that you want to use. So now in the goal seeking control manager, I have two goals and two variables. The two things I'm going to change is going to be the secondary inlet temperature for each heat exchanger, and then I also want to make sure that each heat exchanger results in a heat rate of 640 BTUs per second. So once my secondary inlet temperature is determined, then everything should match up accordingly. So when I click OK, also if it doesn't, then that'll tell you that you have an infeasible solution, and you need to go back to the drawing board and maybe redesign things, or maybe something may not be modeled properly, or maybe measurements might be off. So I'm going to model this, I'm going to run the model here. Took 2 seconds to go through 37 separate iterations on changing that secondary flow rate and getting a solution. So that's pretty quick. So let's take a look here. My variables, I can see that my secondary inlet temperature needs to come in at about 96 degrees Fahrenheit. As long as I have that inlet temperature, my actual heat rate is going to be met that I originally sized for. And if you take a look at the temperature for your resulting, for the outlet of your pipes, you can see that your temperature is 75 degrees Fahrenheit, which is what you needed. And so that's how you can go through sizing a heat exchanger for thermal effects. Any questions on that? All right. Now, all of these concepts, again, that I'm talking about in Fathom, you can do them in Arrow as well. And so they all match. Arrow needs to update to the latest release of Fathom. And actually, that is one of the best ways to solve the majority of your model problems on your computer, is simply updating to the latest release. That'll fix, 7 out of 10 issues that you might experience. Okay, so what we're going to talk about now is we're going to shift gears into sizing, and we're going to start talking more about costs. So Fathom and Arrow have been able to calculate costs for a very long time, and it used to be a separate add-on module, the CST module. Back in Fathom 8, we rolled in that cost calculation module directly into the Fathom and Arrow software itself. And so the cost calculations you can calculate are material costs, installation, maintenance, and energy costs. You can apply any of these costs to basically any junction, pipe, or fitting within the software. And so that allows you to calculate your whole system costs. When you're dealing with cost calculations, you're going to be dealing a lot with databases. There are two types of databases with the software. There's what we call engineering databases, and then there's cost databases. So an engineering database, that contains the engineering information itself. Your pump curve, your heat exchanger resistance curves, your loss factors for elbows, your loss factors for orifice plates and valves. So all of that loss information and whatnot is going to be contained within an engineering database. What you would then need to do is take your cost database and associate it with that engineering database. So you can't have a cost database that's not associated to anything. It's like, what's the cost of pipe? Well, what kind of pipe? What size? And so they work together. And so this diagram here gives you a bit of an idea of how things work together. You can have as many engineering databases as you want. So maybe you've got one engineering database for pipe materials. You've got an engineering database for your valve components, an engineering databases for all your pumps, an engineering database for your heat exchangers. Or you could keep all those engineering databases all in one. Then you can have also multiple cost databases for each engineering database. Why might you have separate cost databases associated with a single engineering database? Different vendors. So if you want to compare costs of one vendor to another, you can do one scenario where you use one vendor's cost, and then another scenario where you do the other ones. Maybe you're doing different monetary costs. So dollars here in America, rupees out in India. And so that's another reason why you would potentially have multiple cost databases associated with a single engineering database. Now, you're going to want to get good at this stuff. And once you build a engineering database and a cost database, once or twice, you'll find that it's actually really easy. It's just a bit tedious. So once you do it, it's not complicated anymore. It just takes a little bit of time. And we are actually working on different ways to streamline that whole process. And the reason why you want to get good at this is because when I talk about automated sizing, you want to reduce those costs as much as you can so that you have a really good design. And so you're going to be using cost and engineering databases a lot with that capability. So in order to turn on your cost calculations, I'm going to close out of the internet here. You just go to Analysis and then Cost Calculation. And if you only care about energy costs, you can do just pump energy only. That'll save you a little bit of time, or you can calculate full system costs. If you click on calculate or energy, then you bring up the cost settings window. And the cost settings is where you define what your energy cost information is. And then you specify which costs you actually want to calculate. Material, installation, maintenance, operation, and energy cost. You can define system lives as well as inflation rates and interest rates. Your time period does not have to be in years. Your time period could be minutes, seconds, hours. Maybe you want to compare the costs for running your pumps at peak times versus off-peak times. So that's why you might use different time periods on that. That's all you have to do in order to turn on the cost calculation capabilities. What I'm going to do right here is I'm going to open up an existing model of our hot water system that we have included with the Fathom Examples help file, but I have already modified it slightly to be a bit more exciting, because in the Examples help file, the pipes are very short, they're really small diameter pipes, so I wanted to scale this up a little bit so that the costs are a lot more, so it's a bit more exciting. So let me go ahead and open that model up here really quick. Okay. All right, so we have two systems here, and we are going to only do energy costs for right now. If you open up the cost settings window, I've got my energy cost at 10 cents per kilowatt hour, and I want to compare my cost savings for using VFDs on my pumps versus control valves. And so I'm running it for off-peak hours for a year. For a year. So that's 4,400 hours. So on my left-hand side of the system, each of these pumps are going to be operating at 100% speed. So they're just cranking as best they can. If you want a cost to be calculated for a particular pipe or a junction, you just have to go to the cost tab and make sure that it's included in the cost report. You can do that globally, so you can set that up for everything at the same time. My control valves are forcing, the normal operation is 1,500 gallons per minute through each heat exchanger. So the off-peak flow is only 1,000 gallons per minute through each heat exchanger. So I've got 1,000 GPM through each flow path there. And then on the right-hand side of the system, what I have done is I have failed open these control valves. And so they're not controlling. Just need to change that. Oh, I know. Okay. All right. So, yes, it's 1,000 gallons per minute through each flow path there. So even though my set point on the right-hand side says 1,500 gallons per minute, this is not going to be used because I've set a special condition to fail that open. So the control valve is not even there. The flow rate is going to be picked up from the pump. So each of these pumps here are going to operate on a VFD where I set my flow set point to 1,600 or to 667 GPM. That times 3 is going to be 2,000 gallons per minute. And so this will show you how much money you're able to save using VFDs. So when I go to run the model here, I can go to my cost report. And as you can see, when you use control valves, your costs are going to be a lot higher than if you were to just use a VFD. So here I've saved a couple $100,000. And so that's an example of how you can show the savings by using VFDs. Is that better? I've never been good at being able to add up numbers really quickly in my head, so that's what the costs look like. Any questions on doing energy cost calculations? Let's step it up in difficulty a little bit here. Let's talk about how you can calculate the entire costs of your system. If you were to run Fathom and go to the Help menu, followed by Show Examples, it'll pull up our examples help file. So you just go Help, Show Examples, pick your favorite units, and that pulls up our help file. The next two examples I'm going to discuss are these two right here. It's our two cost calculation examples. The top one is a beginner cost calculation example. The second one is more advanced. Here's how they're different. The first example, that's beginner, it's going to have you simply access pre-built databases to do your cost calculations that already exist. So you're not having to build those databases from scratch. So we're going to do that one first. The second example has you actually build the cost databases from scratch. Okay, so we've got our cost calculation beginner example, and we've got this heat exchanger system. We want to determine what the material, installation, and energy costs are going to be over a 10-year period. And so there are a number of databases that are used in this example. The databases that are used is going to be one pre-built engineering databases that contains your pipe material information. Then there's also going to be two pre-built cost databases. So you're going to have costs for your pipes and then costs for your components. So let me go ahead and open up this model here. Okay, let's see. Filter things out a little bit, make it a little bit cleaner. Give me just a sec. Erin has a lot of databases that she's used. There we go, okay. All right, so here's our system. It's all set up, and I don't have any costs that are loaded in yet at this time. So the first step that you would do is you go to Analysis, and then let me turn off these other modules. Okay, so you go to Analysis, Cost Calculation, and then you would click on Calculate. So that's done. Next thing is to set up your cost settings. I'm going to use 10 cents. Is it 10 cents per kilowatt hour? 6 cents per kilowatt hour. So that's my energy cost. So this is like costs from 15 years ago. And then I'm going to calculate material and installation and energy cost over a time period of 10 years. So that's the first step, is to set up that cost information. Now, again, I want to calculate what the costs are of my pipes as well as my components. All that information already exists in various engineering databases. So what you would do next is you would load in your engineering databases, which the piping one makes it easy on you because it's already using the steel pipe material database that's included with Fathom itself. So the engineering database for your pipe costs is going to be just steel ANSI pipe. And then there's an engineering database that has your heat exchanger costs as well as other things. So what I'm going to do is I go to database, and here's how you load in a database file. You go to database manager, and so my steel ANSI pipe material database is already available and it's connected. That's going to be the engineering database for my pipes. The next thing I'm going to do is I'm going to add an engineering database, and I'm going to load in the database for my controlled heat exchanger example components. So if I click open, that will add it to the list and it will connect it. If I click on this database and then click on review content, you can see what information is in there. So it's got component information. So this tells me that I have information for, I have engineering information for my branch junction, heat exchanger junction, pump junction, and my three-way valve. So that's my engineering database. The next thing I'm going to do is I can now load in my separate cost databases. So for my edit available list, I go to add cost database, and I have two cost databases that I'm loading in. There's my controlled heat exchanger temperature example costs, and then this one as well for my piping costs. Oops, wrong button. So it's going to use that one. Said it's already available. It's not supposed to be available. So I'm trying to load in the cost information for my pipes, and it's telling me that cost database is already available, but I don't see it in this list. So we'll just keep marching forward here. Now, you've loaded in your engineering information and your cost information. Now what you need to do is set all these junctions to use that information. So what I'm going to do is I'm going to open up my pump, and I'm going to go to my database list, and I'm going to choose use the pump from the controlled heat exchanger example. And that's going to set it up for the appropriate engineering database to get the right costs calculated. Same thing here for the three-way valve. And then for the branch junctions, you're going to do the same thing, and you'll do the same thing for the heat exchangers as well. You can do that through global edits. So for all my branches, they're all going to use that. And then for my heat exchangers, I'm going to do the same thing. Okay, so now I've got my engineering information for all my components so that their costs can now be calculated. Now all I need to do is include everything to be done in the cost report. So I'm going to do that for pipes first. All my pipes. I'm going to include them in the cost report. And then the same thing for junctions. Actually, the junctions, you got to do the types at the same time. So there's my pump, my throughway valve, my branches, one more, and my heat exchangers. Okay, so now everything's set up for doing the costs, and so when I go to try and run my model here, it'll calculate everything. Ignore the warnings, they're not pertinent. And there's your cost report. And it breaks everything down in a very nice pipe by pipe, junction by junction basis. And so it's got a total cost for this system is going to be $75,000. And so it subtotals everything. There's your material costs, your installation, operational energy, which comes from your pumps, and there you go. So again, that's how you go about building, or that's how you go about importing in pre-existing databases that already have engineering and cost information for them. And again, if you go to the cost calculation beginner example, the help file will walk you through that process. Now, I'm not going to take the time to show how to go through building the cost databases themselves, because it is a bit of a process, but I'll just show a quick example here. So let's say that you don't have any cost information into the model yet. What you would do is, if you're using existing pipe material databases that we already have, then in that case, the engineering database is already built. So what I would do next is for the piping costs, I'll go to database. I do need to turn on my cost calculations here first. Come on. So let's say it's 10 cents per kilowatt hour, material, installation, operational energy, 10 years. So after you do that, again, your engineering database for your pipes are already set by the existing pipe material database. So the next thing you do is go to cost database. This is where you build your cost database for your pipes, your junctions, your fittings. So what I would do is I would click on new, because I'm going to create a new cost database. Here's where you would choose which engineering database that you want to associate this cost database with. My pipes are already done, so I'm going to associate my piping costs with this database. If I was doing components and I had my component database in there, which happens to be this one, my heat exchangers and pumps and valves, they're going to use this engineering database information for those costs. So after I choose my engineering database that I'm going to associate the cost database with, you would then give it a description, pipe costs. You can type in whatever notes that you want. Then you go to pipe materials, and this is where you would click on the drop-down menu and you would enter your cost information for your various pipe materials, your different nominal sizes, your different types. And so for example, let's say I'm going to do an 8-inch cost and it's schedule 40. Once I choose that type, I'm going to click on new cost. And for this one, I'm going to give it a description, material cost. And you can do cost per length or cost per weight. Maybe this is $10 per foot. There's my material cost. I can add on another cost. Maybe this one is going to be installation. Install cost. And then give that a cost. Maybe it's $15 per foot. So you would go through the process of specifying your material, installation, maintenance costs for each of your pipes. If you wanted it to be easier, you could assign the same cost for all 8-inch pipe materials, but then in reality, the costs are going to be different for your different schedules. So that's why you wouldn't want to necessarily do it this way. And so after you go through that process of assigning your costs to the various schedules, that's how you build your cost database. We also have cost scale tables. So let's say that you wanted to do, each of the pipes have additional fittings and losses. So for example, this pipe here, it's got some elbows in that pipe that are not actual junctions, and you still want to account for these costs. You can. And so the way that you would do it is by going into database, cost database. The fittings and losses that are included in our software, if you're using that as your database, when you click on new, then you're going to use the default internal Fathom database for those pieces of engineering information. At that point, you can go into your tables and you can do a cost scale table, where maybe here it's going to do a cost per diameter. And so through this table, you would do your cost of your elbows as a function of their diameter. And you don't have to do every single diameter because Fathom will interpolate between those costs for you. But if it's non-linear, then you're going to want to add more data points. And so then once you do this, that builds your cost database for all those fittings inside the pipes themselves. So as you can see, it really is pretty easy. It's just one of those things where you got to do it once or twice, and that gets you used to it, and then it becomes a lot more streamlined. Now, we're going to finish up here with the fact that when you're trying to go through and figure out what your costs are for your system, it's not enough to just know what the costs are. You want to try and reduce those costs. And so there are several ways that you can do it. You can try and reduce either your initial costs or your life cycle costs, or maybe you want to minimize your energy usage or your piping weight. So that's our job as engineers, is to try and minimize those costs as best we can. And so right now we have two other products called AFT Mercury and AFT Titan. They are basically Fathom 7 and Arrow 4 on very strong performance enhancers. So what they will do is they will go through and automatically size all of the entire pipes in your system in order to minimize your costs. You can minimize either recurring costs or non-recurring costs. And so let me show you a quick example with a spreadsheet here. Let's see. Okay, so let's say that you have a very simple system. It's a 1,000-foot long pipeline that requires 8,000 gallons per minute, and your pump efficiency is assumed to be 65% efficient. You know your friction factor, your energy rate is 1 cent per kilowatt hour, and it's a 5-year system life. And you want to determine the pipe size in order to either minimize your initial costs or to minimize your life cycle costs. So if you only have a single flow path that you're dealing with, it's pretty easy to do this with a spreadsheet. So here we have all of our knowns. There's your pipe length, your flow, your efficiency data, etc., etc. Then what you have here is your piping costs for material and installation as functions of their diameter size. And then you also have your pump costs. So you've got material and installation as a function of the pump horsepower. Next, when you go through and set up this database here, you've got your column of different diameters, and then you have your cost per foot, because you know what the length is, and then we know what the volumetric flow rate that we want is, and so that calculates your pipe velocity. From your velocity comes your head gradient, which then leads to your head loss, and then that allows you to calculate what your overall piping costs are, followed by your horsepower required from each of your pumps at the different diameters. And then you've got your pump material costs and installation, and you have your energy cost, etc., etc. So what you would do is, after you set up the spreadsheet, you've got your plots of your material and installation costs, and then the total for your piping. So as your pipe materials get larger, so do your costs. Then you have your pump cost. As your pump horsepower gets larger and larger, then so do your costs. And you've got material, installation, and total. You take these costs and then you add them together. And if you're trying to minimize your first costs, you'd have a plot that looks like this, where you have your total piping costs, which is the blue line. You've got your total pump cost, which is the red line. And then when you add those two lines together, you have the green line, which is the pipe plus the pump cost. So, if you're trying to minimize your initial costs, your sweet spot is going to be at a 16-inch pipe diameter. So if you're at a 16-inch pipe diameter, that's going to minimize your initial costs. And so you can see that based upon that, your initial costs are going to be $108,000 right here. Now, if you extrapolate that out and include the energy costs, it's going to be up to $400,000. Now let's talk about minimizing the life cycle costs. When you go to minimize the life cycle costs, it just throws on one more cost type right there, which is the energy cost. So now when you add all these together, your new sweet spot is going to be a 24-inch pipe diameter. So based upon a 24-inch pipe diameter, you are going to have a larger upfront cost, $141,000. However, in the long run, over 5 years, your total costs are only going up to $180,000, which saves you a whole bunch of money versus a system that's going to cost $400,000. Now, when we're engineers and we're not stuck with the operation costs, or